Hi everyone, welcome to Mr. Source tutorial. On our previous video, we consider a general case or condition where the current source is given as shown in this circuit. That's what we did in the previous video, where we are asked to solve for the node voltages using nodal analysis. But if you come to think of it, how about if the voltage source is given in the circuit? How do we solve that? Or does it affect nodal analysis, like in this condition? Yes, of course it affects, which is what we are going to be seeing on this video. So let's get to business. This is a more complex case, I must say, where some students find it difficult to scale through this problem without not having the understanding of what they are going into. When you have a voltage source as shown here instead of a current source, the procedure will change. Generally we apply KCL to solve another problem where we have current source, but here we are having a voltage source. So let's go. There are two cases of which this could occur. The first case is when you have the voltage source applied directly between the non-reference node and the reference node as shown in this circuit, and the second case is when you have the voltage source applied directly between two non-reference nodes. What you need to do first for you to assign the node, that is, this is a reference node. We already know this, where it's always taken from the 8 parts of the circuit. So this is our node 1, this is our node 2, while this is our node 3. Alright, the voltage at node 1 is called V1, the voltage at node 2 is called V2, while the voltage at node 3 is called V3. Alright, in this video we explain what we mean by a reference node and what we mean by a non-reference node. So if you have forgotten, you can quickly go back and review our previous videos for more enlightenment. So we now go on to assign the current. Alright, this current from this voltage source is flowing from the positive this way. Okay. Alright, now if it flows from this voltage source, if it will hit here, it will split here and split this way. So this current that is flowing through this loop is flowing in this direction. Okay. All right. Well, this, if you come here, it will hit this node and split downwards. So it's gonna be in this form. Okay. And this one will come here and hit on this node and split downward. It's gonna be on this form. All right. That's pretty beautiful. So now we are going to label the currents. You can call this your I1. Current I1. You can label the current anyhow respectively. You can call this your I2. Alright. You can call this your I3. You can call this your I4. Now that's pretty cool. Okay, having done that, the next step is for us to define the currents as what we did in the previous video, starting from I1. You can see this I1 is flowing from V1 to V2. The resistor in between is 2 ohms. So I1 will be given by I1 is equal V1 minus V2 divided by 2 here to here, and our I2 will be given by this. Our current I2 is flowing from node 1 to node 3. It's going to give us V1 minus V3, right, divided by the resistance, which is 4 ohm. Okay, and our I3 will be given by this, our current I3 from node 2 to node 0. So our I3 will be given by V2. Our I3 will be given by V2 divided by 8. Okay, we know why this thing is V2 instead of, right? And our I4 as the last, our I4 will be given by this current I4 given by V3 over resistance 6. Okay. These are the value of current across each resistors in the circuit. So as we said previously that we have two cases of which a voltage source can be applied to this circuit. The first case is when the voltage source is applied directly between non-reference node and the reference node. In this case, it's very simple that when the voltage source is applied directly, you just say, this voltage source is applied to the V1. You just say that V1 is simply equals to 10 volts, which is this voltage. Okay, that one is gone. All right, the next step results in what we call a supernode. When the voltage source is applied between two non-reference nodes, that results us to what we call a supernode or generalized node. Right, in this case, the procedure of solving this problem is going to change. We are going to apply both KCL and KVL to solve this problem. So we now circle. The first step we do is for us to circle this supernode out in this manner. Okay. Now this supernode is where our tension is. All right. We are going to apply first KCL to the supernode. So you say applying KCL, that is Kirchhoff current law, to the supernode. Okay, looking at this supernode, you can see that current I1 is going to the supernode, current I2 is coming into the supernode, while current I3 is going out and current I4 is going out. Okay, our eye is focusing on the supernode. So we say, driving the KCL now, like what we did in one of our videos, I1 plus I2, which is going in, is equal to I3, which is going out, plus I4, which is going out. Okay, so we now put in the value for I1, which was already defined here above. So I1 is given by this. I1 is given by V1 minus V2 divided by 2, all right, plus I2, which is given by V1 minus V3 divided by 4, all right, equals to I3, which is given by V2 over 8, all right, plus I4, which is given by V3 over 6. Okay, to make life easy for us, we can split this because it has a common denominator. Okay, to make life easy for us, we can split this because it has a common denominator. So we're going to have V1 over 2 minus V2 over 2, this, plus V1 over 4 minus V3 over 4, this, equals to V2 over 8 plus V3 over 6. All right, after this step, the next step that follows is for us to collect the like terms. So you're going to have V1 over 2, all right, followed by plus V1 over 4, okay, followed by minus V2 over 2, all right. If this one cross this equality sign, you have to be negative. We have minus V2 over 8, all right, followed by minus V3 over 4. If you want to cross this sign, to be negative, minus V3 over 6, all equals 0. Summing this up, that you say we are summing V1 over 2 plus V1 over 4. This will give us 0.75 V1, all right, minus V2 over 2 minus V2 over 8 will give us minus 0.625 V2, all right, minus V3 over 4 minus V3 over 6 is going to give us minus 0.417 V3, all equals 0. Okay, but recall that our V1 was equals to 10, which is what we have here. Our V1 was equal to 10. So putting the value of V1, you are going to have 0.75 into V1 is 10 minus 0.625 V2 minus 0.417 V3 equals to 0. All right. Okay. So 0.75 times 10 is going to give us 7.5. All right. Minus 0.625 V2 minus 0.417 V3 all equals to 0. All right, we now collect like terms and move this 7.5 to the right hand side. It's going to give us minus, so we're going to have minus 0.625 V2 minus 0.417 V3 equals to positive return to negative minus 7.5. Call this your equation 1. Right. Okay, you've just derived the KCL equation for the supernode. All right. The next thing for us to do now is for us to derive the KVL equation for the supernode. So now we are going to say, okay, so going back to the circuit, which is this our circuit, right? There are things we need to do very, very important that will guide us in having our KVL equation. All right. So this is the loop that is enclosed with the supernode. So it's always advisable to draw this loop out in a separate diagram, right? Putting only the voltage source and ignoring any other components. All right. Now this voltage at this resistor is V2, while this is our V3. So this is going to give us something like this. Take note of what we are doing. You know, this is a negative terminal, right? It's a positive terminal, all right, because this is its grounded part. So this is what you're going to have. This is what this place now is what you are going to have here, like this, plus minus 5 volts. All right, this place you say we ignore the other components except the only voltage source. What you have like this. Okay, this is our plus V2, this minus, this is our plus V3, this minus. All right, so applying case VL now in this direction. Okay, what we did in our previous video, you can quickly review our videos to, if you've forgotten it, to know how we go about this. So we are going to have the equation to look like something like minus V2, right, plus 5, right, plus V3 equals 0. So we have a picture of what our KVL is looking like. So we're going to put it down here a little bit. So we are going to say applying KVL, that's Kirchhoff voltage law, to the supernode. All right, our KVL, which was what we have here on this part, is minus V2 plus 5 plus V3. So our case here, which is minus V2 plus 5 plus V3, bringing it down here, you are going to have minus V2, all right, plus 5 plus V3 equals to 0. So we can make any of these subject formula. I choose to make V2 subject formula. So V2 will be equals to V3 plus 5. All right, I call this my equation 2. Okay, see that? So now you're going to put the value for V2 inside equation 1. So you say substitute for V2, okay, in equation 1, which is this equation. So when you see V2, you put this value which is here, this is equation 1. So you're going to have minus 0.625 into V2 is given by, put this value, V3 plus 5, okay, close that bracket, plus minus 0.417 V3 all equals to minus 7.5. All right, so we can simply find our V3 from here using step-by-step process. So we're going to have, opening this bracket, we're going to have minus 0.625 times V3 give us 0.2625 V3 minus 0.625 times 5 is going to give us minus 3.125. all right, so you have this, you have this minus 0.417 V3 equals to minus 7.5. so you're going to have minus 0.625 V3, right? Bringing this one down, minus 0.417 V3 equals minus 7.5. This negative cross the sign, it on to positive, plus 3.125. okay, all right, summing this together, minus 0.625 V3 minus 0.417 V3 is going to give us minus 1.042 V3, okay, equals to minus 7.5 plus 3.125 is going to give us minus 4.375. okay, so now make V3 subject of formula. Our V3, dividing both sides by that, V3 is going to give us minus 4.375 divided by minus 1.042. okay, so this cancel this cancel this divided by this is going to give us 4.2 volts approximately. all right, we have gotten the value for V3. To find our V2 now, we're going to say substitute the value of V3 in equation 2 is here, right? Equation 2. So we are going to have V2 equals to V3 is 4.2 plus 5. This is going to give us 4.2 plus 5 is going to give us 9.2 volts. okay, so that's the value for the node voltages. Remember that our V1, that's voltage at this node, voltage at node 1, V1 was equal to 10 volts. Now V1 was equal to 10 volts, and our V2, voltage at node 2, is given as by V2 is 9.2 volts, and our V3 is given by 4.2 volts. okay, so this is the value of the node voltages of this, the value of the node voltages of this circuit, this and this and this. So these are the values of the node voltages of this network. The voltage at node 1, which is V1, which is given by the values, and voltage at node 2, voltage at node 3. all right, so in our next video we're going to be seeing a more complicated problem of the super node system. So please, if you are new, subscribe to our channel for more videos. Thank you.